In this lesson, we're going to take a look at force and change in momentum. We know from Newton's second law that net force is equal to mass times acceleration. But we also know acceleration is just rate of change of velocity. So we could say net force is equal to mass times change in velocity divided by time. We just replaced acceleration with change in velocity divided by time. But m times v is momentum, so m times delta v is change in momentum. So now I have net force equals delta p, change in momentum, divided by time. And simply multiplying both sides of this equation by time allows us to say that net force times time is equal to change in momentum. Now that's really kind of a handy equation because we don't have to know the acceleration or even the initial and final velocities in some cases, if we're looking at mass changes, to know how much force has been applied, or we can say how much the momentum changes if we know how long the force acted. So let's take a look at an example problem. Say you're riding in a car and it has a total mass of 1,500 kilograms. And it's got to go from moving at, say, 4 meters per second to rest. Okay? In that case, the change in momentum is equal to final momentum minus initial momentum, which is equal to final 1,500 times 0 minus initial 1,500 times 4, which equals negative 60 or 6,000, I guess, kilogram meters per second. So the momentum has to change by negative 6,000 kilogram meters per second if this car is going to come to a stop. But there's a variety of different ways we could get that to happen. It's going to take a force, and that force is going to have to act through some amount of time, but we can do this over a long amount of time, or we can do this over a short amount of time. So for instance, if I say we've got a time of 20 seconds to get this to happen, then we can see that since force times time is equal to change in momentum, we could say F times 20 is equal to 6,000 divided by 20 divided by 20, and we get F equals 300 newtons, okay? Which is not a lot of force. But if we wanted this to take only 0.2 seconds, we needed to stop very, very abruptly, then force times time equals, and this is of course negative, our negative 6,000 kilogram meters per second. Well, then what we see is F times 0.2 equals negative 6,000, and when we do this division, F equals 30,000 newtons. It is of course negative. So that is quite a big difference, going from 300 newtons of force to 30,000 newtons of force, and that's because we needed a whole lot less time to do it. So we can get the car to stop over a long amount of time with a small amount of force, or we can get the car to stop pretty much immediately, but it takes a whole lot more force. And if you're riding in one of these cars, this is a whole lot more comfortable than that. So we can use a smaller force over a longer time to get the same change in momentum as a big force over a short amount of time. Now, it is worth noting that our units here, newtons, a newton, remember, is mass times acceleration, which is a kilogram times a meter per second per second. Well, if we multiply that by a second, one of these seconds cancels, and we do have kilogram meters per second. So it is true that if we take force times time, dimensionally speaking, or with our units, that we do end up with the units of momentum.